Okay, welcome to the class. From today on, we're going to have a look at a new chapter, chapter 3, uniform circular motion. So there are 4 sections in this chapter. Inertia and non-inertial frames of reference, centripetal acceleration, centripetal force, and rotating frames of reference. So today is the first lesson of chapter 3. We're going to have a look at inertia and non-inertial frames of reference and centripetal acceleration. Okay, think about riding on a bus. When the bus moves at a steady speed without changing direction, you could close your eyes and possibly not even be aware that the bus is moving. If you place a ball in the aisle of a bus, the ball does not move relative to the bus, as shown here in figure 1. When the bus slows down, however, you will see the ball roll forward. When the bus speeds up again, the ball will roll backward. When the bus turns, the ball will roll to the side. So what forces cause the ball to accelerate? The fact is, no forces act on the ball to accelerate it. So a person on the bus will view all motion from the point of view of the bus. So to her, the moving bus in figure 1 is a moving frame of reference. A frame of reference is observer's choice of coordinate system, including an origin for describing motion. A person standing on the sidewalk is in the stationary frame of reference of the ground. In many cases, people use the ground as a frame of reference, especially when they are not moving with respect to the ground. When you are at rest in a frame of reference that has a constant velocity, whether that frame is itself at rest or velocity equals 0, or moving with a non-zero velocity, your velocity relative to the frame is 0. When the bus is moving at a constant velocity, no net force acts on it. Therefore, no net force acts on you inside it. Newton's first law of motion, or the law of inertia, states that any object moving at a constant velocity, including velocity equals 0, remains at that velocity if no net force acts on it. The bus in this case is an inertial frame of reference, which is a frame of reference in which the law of inertia is valid. Now think about what happens when the bus slows down and the ball begins to roll forward inside the bus. What causes the ball to move forward? As the bus slows, it accelerates, which means changes velocity in a direction that is opposite to the direction of motion. Therefore, the bus is no longer an inertial frame of reference. It becomes a non-inertial frame of reference, which is a frame of reference in which the law of inertia is no longer valid. The reason there appears to be a net force on the ball is that the ball continues to move with the same velocity it had before. Obeying the law of inertia, the ball does not immediately slow down with the bus, which is shown here in figure 2. Within the accelerating bus, or non-inertial frame of reference, this looks as if a force is pushing the ball forward. Similarly, when the bus starts from rest and speeds up, the ball tends to stay at rest. To you and other passengers in a non-inertial frame of reference, it appears as if there was a push on the ball toward the back of the bus. There also appears to be a force on the ball when the bus turns a corner. The ball continues moving in the same direction as the bus before the turn. From your point of view in the bus, this would be like a force pushing the ball in the direction opposite to that in which the bus was turning. So to explain these various motions, we invent ideas of fictitious forces. Fictitious forces are apparent but non-existent forces that explain the motion in accelerating or non-inertial frames of reference. In the bus example, a fictitious force pushed the ball in the direction opposite the acceleration of the bus. As you continue learning about mechanics, you will encounter other fictitious forces. Fictitious forces simply explain non-accelerated motion in accelerated frames of reference. So now let's have a look at a tutorial which shows how to solve problems involving an object placed in a non-inertial frames of reference. Okay, so let's consider this tutorial here. Okay, first let's have a look at sample problem 1, calculating the acceleration of a non-inertial frame of reference. So we have a teacher suspends a small Coke ball from the ceiling of a bus. When the bus accelerates at a constant rate forward, the string suspending the ball makes an angle of 10 degrees with a vertical. Can you calculate the magnitude of the acceleration of the bus? Okay, I'll give you 5 minutes to think about this question by yourself, and then we'll have a look at the solution together. Okay, first of all, you should draw a free body diagram to illustrate this question, okay? All right, have you finished? So let's have a look at the solution here. So we can draw a free body diagram like this. And look at the situation from an Earth frame of reference. Draw an FED to show the forces acting on the cork ball. Then the horizontal component of the tension, Ft, balances the acceleration. So express the components of the tension in terms of the horizontal and vertical applied forces. Then we can calculate the magnitude of the acceleration. So the vertical components of the force, Fy, sum of Fy equals 0, right? And this gives us F tension cosine theta minus Fg equals 0. So the tension force equals mg over cosine theta. Then the horizontal components of the force, sum of Fx equals ma. A is acceleration of the cork ball. Then we have tension times sine theta equals ma. And then substitute Ft equals mg over cosine theta. This gives us mg over sine theta over cosine theta, then times sine theta equals ma. Then we can cancel m on both sides of the equation. That gives us g times tangent theta equals a. So a equals g times tangent theta. And put all the values in, we have a is acceleration is approximately 1.7 meters per square second. So the magnitude of the bus acceleration is 1.7 meters per square second. Okay, any questions? All right, good. If no questions, let's have a look at another concept, which is called apparent weight. So the study of vertical acceleration can also introduce fictitious forces. To understand this, consider what happens when you stand on a bathroom scale, which is shown here in figure 4a. As in all cases, when you stand up, you feel a force pushing upward against the soles of your feet. This is the normal force, and it is equal and opposite to the weight, or mg, of your body when you stand on level ground. Now, suppose that you stand on the same scale inside an elevator. When the elevator is at rest, the normal force is again the same as your weight. This is also true when the elevator is moving at a constant non-zero speed, upward or downward. However, what happens when the elevator accelerates? When the elevator accelerates downward, the normal force decreases so that the magnitude of the reading on the scale should be less than your weight, right? Which is shown here in figure B. Similarly, when the elevator accelerates upward, as you can imagine, the normal force would increase, resulting in a greater reading on the scale. As with the bus at the beginning of this lecture, the elevator can be an inertial frame of reference when it has a constant velocity going up or down, or when it's at rest, right? It becomes a non-inertial frame of reference when it accelerates, resulting in a normal force that is either greater or less than your weight. The magnitude of this normal force in a non-inertial frame of reference is called apparent weight. So other non-inertial frames of reference produce other values for apparent weight. On a free fall ride at an amusement park, the acceleration of the ride is equal to g. And the normal force is 0, which is shown here in figure 4C. Thus, the scale will read an apparent weight of 0. Similarly, an astronaut aboard the International Space Station is constantly in free fall. Therefore, the normal force acting on the astronaut is actually 0, which is shown here in figure 4D. Okay, next, let's have a look at another tutorial in which we'll learn how to solve problems that involve the apparent weight of an object in a non-inertial frame of reference. Okay, so let's consider this problem here. An elevator accelerates upward with an acceleration of magnitude 1.5 meters per square second, after which it moves with a constant velocity. As the elevator approaches its stopping point, it undergoes a downward acceleration of magnitude 0.9 meters per square second. Can you calculate the apparent weight of a passenger with a mass of 75 kilograms when A, the elevator undergoes positive acceleration, B, the elevator moves at a constant velocity, C, the elevator undergoes a negative acceleration? Okay, here I'll give you 10 minutes to have a look at this question by yourself, and then we'll have a look at the solution together. You can start now. Okay, let's have a look at the solution together. Okay, in question A, first of all, we can draw a free body diagram of the passenger. All right. And solve for the normal force. Use up as positive. Okay, so here, this should be FG. This force should be F3. Okay, so according to the FBD, we have the following relationship. Fn minus Fg equals ma, right? Because the elevator undergoes positive acceleration. So we have Fn equals mg plus ma, which is 75 kilograms times 9.8 meters per square second plus 1.5 meters per square second. And Fn is 8.5 times 10 raised to the power of 2 newtons. The apparent weight of the passenger is 8.5 times 10 raised to the power of 2 when the elevator undergoes positive acceleration of 1.5 meters per square second. And in question B, we know that in an inertial frame, there is no acceleration, so the apparent weight of the passenger is just mg. Because the net force is just 0, right? So Fn equals 4.7 times 10 raised to the power of 2 newtons. So the apparent weight of the passenger when the elevator moves at constant velocity is 7.4 times 10 raised to the power of 2 newtons. And in the situation C, again, we can draw an FVD of the passenger and solve for the normal force. So this time we have the net force along the vertical axis equals ma, which gives us negative Fn plus mg equals ma, and Fn is mg minus ma. So that is 6.7 times 10 raised to the power of 2 newtons. So the apparent weight of the passenger when the elevator undergoes negative acceleration of 0.9 meters per second per square second is approximately 6.7 times 10 raised to the power of 2 newtons. Okay, any questions? All right, good. If no questions, that's the first part of this lesson. We can take 10 minutes break. And after that, we'll have a look at the second part of this lesson, which is about the centripetal acceleration. Okay. All right, you can take 10 minutes break now. All right, welcome back. Let's continue our lesson. Now let's have a look at the second part of this lesson, which is about the centripetal acceleration. So here, as shown in figure 1, the hammer throw is a track and field event in which an athlete throws a hammer, which is a heavy metal ball attached to a wire and handle, the farthest distance possible. To do this, the athlete first swings the ball in a circular path. After giving it its maximum circular speed with 3 or 4 turns, the athlete releases the hammer, which then flies down the field. Just before the hammer is released, it had uniform circular motion, which is motion in a circular path at a constant speed. By moving the ball in a circle, the athlete introduces force of tension in the wire. This tension keeps the ball in a circular path. The greater the tension, the greater the acceleration towards the center of the circle, and the faster the ball moves in a circular path. When the tension is very large, so is the speed of the ball. When the athlete releases the ball travels far down the field. You might not always realize it, but objects moving in circular paths are all around you. Clothes in a washing machine during the spin cycle, the drum of a clothes dryer, the hands of certain electric clocks, and the spinning blades of a blender and lawnmower. All of these objects move with uniform circular motion. What you might not have considered is that these are all among the most common non-inertial frames of reference. These objects move in a circular path, so their velocity constantly changes direction. Therefore, they are accelerating, right? Acceleration that is directed towards the center of a circular path is called centripetal acceleration, which is usually denoted by AC. Okay, so next let's have a look at the equations for centripetal acceleration. Recall that the average acceleration AV of an object equals the change in velocity delta V during an interval of time delta T, which is given by this formula. The average acceleration equals the change in velocity delta V over the change in time delta T. For an object moving with uniform circular motion, the velocity changes direction continuously with time. So delta V is definitely not 0, right? Therefore, the centripetal acceleration is not 0 either. To calculate the centripetal acceleration, we now consider the example of a runner moving at a constant speed along a circular track. The velocity of the runner changes with time and is always tangential to the circular path, as shown here in figure 2. Figure 2a shows a runner's velocity vectors at 2 nearby positions, which are A prime and A. Well, figure 2b shows the corresponding change in velocity delta V over a short time interval delta T. Also recall from section 1.4, which we have discussed previously, that the difference in velocity vectors is the same as adding one vector to the negative of the other vector, right? So we can shift vector v2 down so that its head is at point A, which is shown here in figure 2b. Then reverse v1 so that v1 becomes negative v1. And then place the tail of vector negative v1 at the head of vector v2, so that the sum of the vectors is delta v, which points toward the center of the circle. It should be noted that we actually need to decrease the size of the time interval until it is very small for delta v to point directly toward the center. For the sake of discussion and illustrating the concept, however, our model in figure 2 is satisfactory. As we can see in figure 2a, the individual velocity vectors v1 and v2 are both tangent to the circle, perpendicular to the circle's radius, and equal in length or magnitude. This is true for all the runner's velocity vectors along the circular path. The acceleration vector has the same direction as delta v, so it follows that the centripetal acceleration of an object must always point towards the center of the circular path. Okay, now use the triangle BAC in figure 2b to calculate the magnitude of the acceleration. This triangle has two sides with equal lengths, which means this triangle is isosceles triangle, right? Two equal lengths are the magnitudes of v1 and v2. In general, the velocity magnitude is the same at any point around the circle. So the magnitude of v1 equals the magnitude of v2 equals the magnitude of v. Or simply, we can denote that a magnitude as the letter v. The third side of this triangle is a vector delta v, which has the length of the magnitude of delta v, right? So the triangle BAC has the same interior angles as triangle AOA prime. In figure 2A. So these triangles are similar. You can check this by using the relations below to show that the angle theta is actually the same for both triangles. Also note that in figure 2b, that the angle at point A between vector v2 and the radius is 90 degrees. So we have the following relationship. Half of theta plus alpha equals 90 degrees, which means theta plus 2 alpha equals 180 degrees, which means theta equals 180 degrees minus 2 alpha. When you add the two equal angles, alpha, within triangle BAC to the third angle, they equal 180 degrees. So the third angle must equal 180 minus 2 alpha equals theta. Two sides of triangle AOA prime are along the radius of the circle, which is shown here in figure 2A, so that they have the length R, right? While the other side between points A prime and A has length S. When delta T is very small, the arc length between point A prime and A approaches a straight line length that connects A prime and A. Therefore, the distance the runner travels from A prime to A is approximately equal to the distance given by S, which is approximately V delta T. The triangles BAC and AOA prime are similar, so the ratios of their corresponding sides are equal. Substituting V for the magnitude of either V1 or V2, and assuming a very small delta T, then we have the following relationship. The magnitude of delta V over V equals S over R. And eventually we have the magnitude of delta V equals V squared times delta T over R. So the magnitude of the average acceleration equals the magnitude of the difference in the velocities, delta V, divided by delta T, right? So the average acceleration, AV equals the magnitude of delta V over delta T, which is given by V squared delta T over R, then over another delta T. We can then cancel the delta T, which gives us the magnitude of the average acceleration in the uniform circular motion. A average equals V squared over R. V is the magnitude of the linear velocity. So in the above equation, the average acceleration equals A centripetal, which means the centripetal acceleration when the time interval is very small. So we have the following relationship eventually here. Okay, this is a first formula you need to remember. The centripetal acceleration in the uniform circular motion AC equals V squared over R. Again, this is just the magnitude, okay? The direction of the centripetal acceleration is always pointing to the center. Okay, in this formula, as we have just discussed, AC denotes the magnitude of the centripetal acceleration. V is the speed of the object moving along the circular path, well, which is actually the linear speed of the object moving along the circular path. And R is the radius of the circular path. Note that although this derivation started with the definition of average acceleration, the result becomes exact for a very small time interval delta t. So the centripetal acceleration in this case is an instantaneous quantity directed towards the center of the circle. Okay, and also note that because we have this relationship, the linear speed V equals the angular speed omega times the radius r, right? Therefore, if you substitute V using omega r, then we have another formula to calculate the centripetal acceleration, which is omega r squared. In this formula, AC also denotes the centripetal acceleration, but this time omega denotes the angular speed. The unit of the angular speed is in radius per second. And again, r is the radius of this motion. Okay, so the equation for centripetal acceleration indicates that when the speed of an object moving with a uniform circular motion is larger for a constant radius, such as in the case of the hammer in the hammer throw, the direction of the velocity changes more rapidly than it would for a small speed. This means that to produce these rapid changes in velocity, you need a larger acceleration. When the radius is larger for a constant speed, the direction of the velocity changes more slowly, so the object has a smaller acceleration. Okay, so sometimes you might not know the speed of a object moving with a uniform circular motion. However, you might be able to measure the time it takes for the object to move once around the circle, or the period, which is usually denoted by uppercase T. Then you can calculate the speed. Remember that the speed is constant, right? And that it equals the length of the path the object travels, which means the circumference of the circle, or 2 pi r, divided by the period t. So we have the following relationship here. The linear speed, or just abbreviated as speed. Well, in uniform circular motion, when we talk about speed, by default, we mean the linear speed, okay? Otherwise, if you want to mention the angular speed, you should specify that's a angular speed. Okay, so we have the following relationship: the speed v equals delta d over delta t. Then delta d equals 2 pi r, and delta t equals uppercase t, which is a period of this motion. So we have the following relationship: the speed of the motion v equals 2 pi r over t, right? So we can substitute the above expression for v into the above equation for centripetal acceleration to obtain the acceleration in terms of the period and radius. Then we have actually derived a new formula to calculate the centripetal force considering the period, which means the centripetal force, the centripetal acceleration AC also equals 4 pi square r over t square. Okay, this means if you do not know the speed v, but you do know the period of this motion, you can also directly find the centripetal acceleration using the period t, okay? Okay, on the other hand, for high rotational speeds, frequency is preferred quantity of measurements instead of period. So the frequency, which is usually noted by lowercase f, equals the number of revolutions per unit of time, or by this relationship here, f equals 1 over t, right? So again, if you know the frequency instead of the period, we can also have another form of formula to calculate the centripetal acceleration, which means the centripetal acceleration AC can also be calculated using 4 pi square RF squared, which is shown here in this formula. Okay, so the SI unit for the frequency is hertz, which is abbreviated as Hz, or cycles per second. So you need to be careful. There are 4 formulas we can use to calculate the centripetal acceleration for a uniform circular motion, okay? First one is here. Second one is here. Third one, and the fourth one. Depending on which input you have, whether you have a linear speed, angular speed, period, or frequency, you can refer to different formulas, but the essence, the nature of these formulas are actually the same, right? Okay, so in a summary, we now have 4 equations to determine the magnitude of the centripetal acceleration. When dealing with vectors of this acceleration, remember that centripetal acceleration always points toward the center of the circle. Okay, now let's have a look at some sample problems to show how we can solve problems involving the centripetal acceleration. Okay, now let's consider tutorial 1 here. Okay, sample problem 1 in this tutorial, calculating the magnitude of centripetal acceleration. A child rides a carousel with a radius of 5.1 meters that rotates with constant speed of 2.2 meters per second. Can you calculate the magnitude of the centripetal acceleration of the child given this information? Okay, I'll give you 5 minutes to consider this problem, and then we'll have a look at the solution together. All right, I think you should finish now. Let's have a look at the solution together. So this question is pretty straightforward, right? We are given the following information. We know the radius of this uniform circular motion, which is 5.1 meters. And the speed of this motion is 2.2 meters per second. And we need to calculate the centripetal acceleration AC. Okay, so this time, because we know the speed or the linear speed, so we can refer to this formula: centripetal acceleration equals v squared over r, right? And put all the values in. That is 2.2 squared over 5.1. So the centripetal acceleration AC, well, specifically speaking, the magnitude of the centripetal acceleration AC equals 0.95 meters per square second. So we know the magnitude of the centripetal acceleration of the child is 0.95 meters per square second. Okay, then let's, do you have any questions? No? All right, then let's have a look at another sample problem. Here, a salad spinner with a radius of 9.7 centimeters rotates clockwise with a frequency of 12 hertz. At a given instant, the lattice in the spinner moves in the westward direction, which is shown here in figure 3. Determine the magnitude direction of centripetal acceleration of the piece of lattice in the salad spinner at the moment shown here in figure 3. Okay, I'll give you 5 minutes to consider this problem by yourself, then we'll have a look at the solution together. All right, have you finished? Okay, again, this question is also pretty straightforward, right? So this time we know the frequency of the circular uniform circular motion, so we can refer to this formula to find the centripetal acceleration. AC equals 4 pi square RF square, right? And put all the values in. That's 4 pi squared times 0.097 meters times 12 hertz squared. And then the centripetal force is, the magnitude of centripetal acceleration is 5.5 times 10 raised to the power of 2 meters per square second. And also because this question asks you to determine both the magnitude and direction, right? So in the final statement, you should also specify the direction of the centripetal acceleration, which is pointing towards the center. So the direction is north. Any questions? Okay, if no questions, let's consider another sample problem here. The centripetal acceleration at the end of an electric fan blade has a magnitude of 1.75 times 10 raised to the power of 3 meters per square second. The distance between the tip of the fan blade and the center is 12 centimeters. Can you calculate the frequency and the period of the rotation of the fan? Okay, I'll give you 5 minutes to consider this question separately. And then we'll have a look at the solution together. Okay, you can start now. All right, let's have a look at the solution together. Okay, so we are given the following information. The magnitude of the centripetal acceleration, AC, is 1.75 times 10 raised to the power of 3 meters per square second. And we also know the radius of this circular motion is 12 centimeters, which is 0.12 meters. And we want to find the frequency and the period of this motion. Okay, so we can use equation for centripetal acceleration that includes frequency and radius, which is AC equals 4 pi square r f square. Rearrange and solve for f, right? Then use equation relating frequency and period to calculate the period of rotation, which means the period t equals 1 over f. Okay, so following this logic, the frequency is given by the square root of the magnitude of the centripetal acceleration, AC, over 4 pi square times r. Okay, again, put all the values in. We have F is positive or negative 19.2 hertz. Okay, we only accept the positive value because for frequency, it cannot be a positive number, right? Okay, so we know the frequency of this motion is 19.2 hertz. And then the period of this motion, t, equals 1 over f, which is 1 over 19.2 hertz, which is approximately 5.2 times 10 raised to the power of -2 seconds. Then we can make the final statement like this. The frequency of the fan is about 19 hertz, and the period of this motion is 5.2 times 10 raised to the power of -2 seconds. Okay, do you have any questions? All right, if you don't have any questions, that's the end of today's lesson. Remember to complete the homework on Google Classroom and submit them before the deadline, okay? I'll see you next time.